Sorry, that was an awkward shut off there. I meant to finish this first and I accidentally clicked off. So let's just finish this one. We had just gotten to 1/6 for the answer here to this problem. And that is done. That is our limit. And because the function itself didn't exist, right? We got an indeterminate form when we tried to plug in, but the limit exists. This tells us that there is a hole in the graph. There is no y value, but we have to approach the 0.316 in the limit. That one should actually look a little bit familiar to you. We've done this problem before using a numerical method. This was back on page 9. We found that exact same limit numerically by plugging in values of x that got progressively closer and closer to 3 and looking for the pattern in the numerical values. So we can see an example of a limit that we've done 2 different ways and, of course, thank goodness, gotten the same answer both times. All right, we'll look at a couple more examples of handling indeterminate forms. The next one says combining algebraic fractions. In this case, if I tried to plug in to my original limit, I was trying direct substitution first, I would get 1 over 2 minus 2, subtract 2 over, 2 squared would be 4, minus 2 times 2 would also be 4. That's 1 over 0, minus 2 over 0. Now remember what we said before. When we have a non-zero over 0, that's an infinite limit. So this is the infinity minus infinity case. Also an indeterminate form. Okay. So I need to do some algebra. Anytime I get an indeterminate form, it tells me I've got to pull out some algebra tricks. Again, you guys have a vast store of algebra knowledge. You've taken a lot of algebra in your lives. So always just think back to the various things that you know how to do. In this case, I've got 2 fractions that are being subtracted. You know how to subtract algebraic fractions, right? Get a common denominator. That way we'll be able to combine the fractions. So let's do that. If I factor the second denominator, just pull out an x. It looks like to get a common denominator, all I'm going to need to do is multiply this first one by x over x. Form of 1, so I'm good. And so I'll get 1 times x or x minus 2 over the common denominator x times x minus 2. Now that I've done that, I can see that I'm able to reduce my algebraic fraction, dividing out a form of 1, x minus 2 over x minus 2. Just leaves me with 1 over x. And now I'm ready to try plugging in again. Once I've done the algebraic manipulation, that's when we try substituting our value again. And plugging in 2 is no longer going to be a problem. I'll just get 1 over 2, or 1/2. And so there's my limit. So same argument as before. Originally, when I tried to plug in 2, it was undefined. I had 0 in the denominator. So there is no y value, but there is a finite limit. We have to approach what will be a hole in the graph at the point when x is 2 and y is 1/2. While we're looking at this problem, I'd like to make one more remark about notation. You'll notice that I continue to identify this as a limit. I write the limit as x approaches 2 in each step until I'm actually ready to plug in the value. Then I no longer need to write that. Right? I did the same thing here. I kept on writing that I'm doing the limit until I actually was ready to plug in the x equals 3. That's important. Correct mathematical notation says you got to keep your reader knowing what you're doing. And this is finally the stage where it's no longer a limit, it's actually the solution to the limit. And so I stopped writing the notation. One of the things about math is its notation tends to be very, very precise. And so to communicate math effectively, it's really important to use correct notation. So that's something that I'm going to ask you to try really hard to watch out for and make sure you're writing the fact that you're working on a limit until you do plug in that value. All right, here's another example of a problem that we're going to have to use some algebra on. I want the limit as x approaches -2 for this function. We can already see -2 is going to be a problem, but we'll put 0 in the denominator. But we should go ahead and substitute to find out whether it's 0 over 0 or a non-zero over 0. So let's do that. Plugging in -2 for the x. That's going to give me the square root of 1 minus 1 over 0, which of course is 0 over 0. And so we are back to an indeterminate form again. They're really important because remember, non-zero over 0 is not the indeterminate form. That's the infinite limit. So you got to check and see which one it is. This is the indeterminate, which gives me hope that I can find a finite limit. But I know I'm going to need to do some algebra to try for that. So the little clue on this one says, try rationalizing a numerator or a denominator. In this case, the radical happens to be in the numerator, so we'll rationalize the numerator here. To rationalize, remember that you always multiply by the conjugate. So I'm going to multiply by the conjugate, which would be x plus 3 plus 1. And I can't change the value of my expression. So if I multiply by that on the top, I have to multiply by the same thing on the bottom. I'm multiplying by a great big form of 1, so that I'm not really changing the value of my expression. All right, the beauty of conjugates, of course, is that things work out so well. When I multiply these, the square roots here are simply going to cancel each other out, and I'll get x plus 3. Outers gives me the positive square root, and the inners gives me the negative square root, so those add up to 0. And then I just get a minus 1. The denominator, I'm not going to bother multiplying out. I'm just going to write the product right down here in the bottom. And the reason is we can kind of anticipate. You can see this is going to simplify to x plus 2. So in the next step, I'm going to be able to divide that out with the denominator. So we have 1 over the square root of x plus 3 plus 1. All right, we've done a lot of algebra. This is usually the stage where we want to try plugging in our value again. And since I'm actually going to substitute the value now, I'll stop writing the limit. You'll notice I've written it every step up to this point. But now I'm actually going to plug in. And it's looking good. I don't think we'll get 0 in the denominator this time. In fact, we're going to get the square root of 1, which is 1. 1 plus 1 is 2 in that denominator. And that is going to be our limit. Once again, the original function was undefined. We got an indeterminate form when we tried to plug the -2 in originally. So there is no y value. But we do approach this y value in the limit. So this is a hole in the graph. At the point where x is -2, we approach a y value of 1/2. we'll finish this in the last video, one more video for this section.